This is actually pretty cool. One of the things that happens in stats is that you'll hear the term, the data has been normed. It doesn't mean that some guy named Norm took care of the data. It just meant that there was certain things happened with it. Normally distributed data is what we call a bell curve. You guys heard that before, right?
Yes. Not really.
Well,
I don't understand. Teachers
all right.
That's very nice.
It looks like a bell.
Is that where you give certain people F's and A's? Like what
Their data over the long term of specific types of data, and I have some examples today that make total sense of this, of what they call normed data. Basically what this means is that half of all data is on one side, and half of all data is on the other side. Because underneath the curve is 100% of the data. Convenient. Now, what happens here is that this thing's called the bell curve, because it looks kind of like a bell.
Shocking.
What's like what? Yes, but what goes up must come down. And then you also have to remember that you have normal distribution, and you can also have what's called paranormal distribution. Yes, ma'am.
So it's not real.
I see what you did there.
No, but it is a question.
Paranormal distribution is demographic. Exactly.
All right, so here's what's happening. Normal distribution, what you have to take into account are the following numbers.
Is it always going to be those numbers?
That's why it's important if data is normed, this holds true. Here's what these three numbers mean. In statistics, you've got your average, your mean, if you will. That's the 50% of data is on one side, 50% is on the other. That's where you get the average from. What happens with after that is that you get stuff that are called standard deviations. Standard deviations is another way of looking at the, not magic, but it's a way that you can reference a data point in relationship to the mean. It's another way of measurement of regression to the mean, of how far something is from it. And it's not anything you guys have to worry about calculating. You don't have to do any of that stuff. You're just being told something is a standard deviation away, plus, minus 2, whatever. What happens here is all data, or 68% of all data, are plus or minus 1 standard deviation. 95% of all data, if this is norm, are plus or minus 2 standard deviations. And then this is plus or minus 3 standard deviations. Here's why this is important. When you have your breakdown, and you know that your data, half of it is above the mean, half of it is below the mean, when you start breaking it apart in terms of what we call our standard deviations with these percentages breakdowns, or excuse me, percent breakdowns, you can create chunking within your data. Okay? You can do this. So let me see if I can draw this again. That's not that great. No. All right, so we'll say this is it. Ish. So here's our, within 1 standard deviation, 68% of all data occurs. Okay? It's symmetrical about the mean, which means half of 1 standard deviation is above the mean, and half of 1 standard deviation, or half of the other standard deviation is below the mean. Which means if it's 68% for the whole thing, how much is in each half?
34.
34. So 34% of data occurs here and here, just by taking half of it. All right. Now that's 1 standard deviation plus or minus. If I go 2 standard deviations, that means now I am 95% of all of my data in my chart is plus or minus 2 standard deviations of the mean. Excuse me. Which means, how do I figure out those little slots? Well, all you have to do is subtraction. If 95% is this whole chunk between the two, take out the middle, which was the 68%, and you're left with 27%. You okay with that? Sure. Each of those two chunks would be the same amount of data then, so you just cut that in half. So it's 0.135 for both of these. I'm keeping them in as decimals for right now because it's all going to add up to equal 1 in the end. You all right with that? Now, I do the exact same thing again for 3 standard deviations. Within 3 standard deviations is 99.7% of all data. Well, take 99.7, subtract 95, and I'm left with 4.7. I cut that in half. I know, heavy sigh. And I get 2.35, I believe. But remember, I'm going to move that 2 decimal places over because I'm talking about points, okay? So that gets me 0.0235, 0.0235 on both sides. How much is left after the 99.7%? 0.3. Those are your outliers on the outer edges. So if it's 0.3 on both to add up for both of them, 0.15 here, 0.15 there, which means it's 0.0015 on either side. So this would be 0.0015. And what's nice about saying this idea of this normed data, this standard deviations like this with normal distribution, those numbers will never change. Those percentages never change. Which means if you can take some data set and you're able to normalize it, math becomes really, really fast. And that's what statisticians do a lot with big data sets. If you look like ACTs, SAT scores, you can look up how it'll say your score, and then it'll say, is that much stuff lying around? How do you leave stuff everywhere? You know you left with your laptop because you got it caught on the door.
Yeah, I do. I remember reading that. Where's my binder go?
Did somebody hide it?
No, that's okay.
They got the one we got wrong.
Anybody?
I'm sorry to disrupt. It's okay. No, it's probably not.
We found
See it. Okay. And it's just really easy to harass her. Well, I harass everybody, so you know that. So, when you get to statistics and things, I think you might even see it on your calculators. If you hit the Z, you hit your stats button, you'll see somewhere it says like Z testing and Z scoring and all. There's a lot of these types of statistical inferences that you can do to data sets to normalize stuff. You don't have to worry about doing any of that type of stuff at all in this class. At all. You won't calculate anything. You won't calculate a standard deviation. You won't have to do any of that stuff until you take a stats class. All we're going to do is look at data sets and say, what's the probability of a selected person that falls within 2 standard deviations or something along those lines. Okay. So a really easy example of this is when we talk about, where is it, heights. Let me fill in my chart over here so we can reference it. So it's 0.34, 0.34.
Do we all have to get an order of height?
No.
So I go to bed.
02, is it 0235?
Yeah, doesn't matter.
And then 0015.
It matters to me.
You have to know how to make it. That's why I said, really, that's why I said all you have to know is 68, 95, 97, and 99.7. If you know those 3, see how fast it was to build it? If you remember those 3 numbers, you're fine. Okay. Now here's what happens. Guys, really easy way of looking at this. Heights. The average height of a male is 69 inches tall. All right, 5'9". Apparently this is older data because Trap looked it up and it's closer to 5'10", but whatever. So that means that it also has a standard deviation of 2.75 inches, which means if you start looking at it, if I go up, yeah, the average male height is 6'9".
I'm at 5'9". By like an inch.
Yeah. If I add 2.75 to that, I get what? 71.75 inches. If I add another 2.75 inches, that's up 2 standard deviations. So here's +1. +2 would be, was it 7350? +3 would be at
7450. Wait. Don't listen to me. Yes.
yes, 7450. Thank you.
Great.
If I add another 2 3/4, we get was that 7725? And then if I go the other direction, so this is your X with a bar over it stands for mean, your average. Okay.
It looks like a mean piece.
I subtract out and I get 66 1/4. No, I hate decimals. It's 60. Yeah, 66 1/4.
Stop 7 1/4.
All right, subtract another one. What do you get?
Wait, so you subtract
63. And then I subtract out one last one.
60.75. Wait, so you subtract and add 2.75?
Yep.
Or half?
No, the standard deviation is 2.75. So you add going up and you subtract going down. So just by, yes ma'am. Then that one's right though. Yeah, that should be right.
Oh, whoops. I meant to say 66.
So what that means is, when you're looking at your data set, that's what that means.
Means code is a meme.
Oh, that's. I see what you got.
It's just average.
+1. Anyway, basically that tells you that I'm 6'3". That's 75 inches. If you start really thinking about that,
There's a lot of time.
here's 50% going this way. Here's 34%. Here's another, was it 12, 13? I always think it's 13.
Can we start measuring each other?
If I add these two together, what's that? Well, hold on a second. What I'm getting at here is roughly, give or take, if I work backwards from all of that, that means I'm basically taller than, well, you add these two together, 3%, and then like just about 97% of the population of U.S. males.
Aren't you special?
I'm something. Okay. Now, when you start, that's what happens with some of these numbers. And you don't think about that, but when you look at across large sample sizes, this kind of data stuff happens. So it's just a matter of reading data sets and trying to figure out within standard deviations, because all you have to do is add or subtract what they tell you is the standard deviation. These percentages never change. And that's why we want to work with norm data. Okay. It's really not that crazy.
Well, if you count how many people there are in that percentage, does the size, the amount of subjects you have in a sample size,
Yeah.
it's that's a lot.
Well, if you think about it, all right, rephrase this again. What if the question that was written in this one is, What's the probability that you select 3 people that are taller than 71.75 inches? If I want to select 3 people, what's the probability that all 3 of us are going to be taller than 71.7, almost 6 feet tall? Okay? Now here's what happens. If you want to select 3 of them, is each selection independent of the prior selection? Yeah. So what you're doing here is you're just taking that probability and multiplying it out 3 times. So the probability that you select somebody that is going to be taller than this, well, that's going to be these 3 percentages, isn't it? Isn't that the same as saying 1 minus all of those? It's a lot quicker sometimes to use the complements. Because if I know that once I get to this side here, it's 50% of my data, I'm adding 34%, so I get 84% of the data is to the left, which means how much data is to the right? 16. Okay? So what that means is that you have a 16% chance of randomly selecting a person that's taller than 5'11" and 3/4. Almost 6 foot tall. You just multiply that out 3 times. 16, 0.16 times 0.16 times 0.16. Right. So if you really start thinking about it, the probability of selecting me plus Skoda and
Lofthouse.
well, Lofthouse is in 6 foot 3. He's not that tall. Mr. Wright. All right. Gordon's. Yeah. You start thinking about it. You know, you've got just between like me and Plaskoda. Plaskoda is 6'4".
It's like less than 0.5%.
Yeah. You really start thinking about the randomness of just tall people.
I mean, like, maybe we just have a lot of tall people in Illinois, so it doesn't seem like it'd be like that.
So what's the problem?
Yeah. So what would happen here is I would take this percentage, that 0.16,
I don't know, but I feel like there's a lot of guys who are
and that's how I get that out. Yes, ma'am.
people are tall, everyone's $60 to me.
Hold on.
How you're determining percentages between, can't that go on for a while?
What do you?
Where you just add 0.75?
Yes, but after so long, that's the whole idea of norming data. So once you start getting beyond 3 standard deviations, you're talking about what 0.3% of all data will be your outliers. That's what you're looking at. So yeah, there are technically further standard deviations, but it's already encompassing them because the percentage of them actually being there is so few. The probability of landing in that region is so small.
So it's 0.16 from 71.75 to 7.
Correct. It's 16% from 71.75 to the end. Okay. Because all of this is 100%. If I'm looking from here over, it's just 16% of data. That's all this works out to be. Okay. Normed data. Same idea. You are at a supermarket. Time spent by shoppers at a supermarket is normally distributed at roughly a 45-minute average.
How come I'm in there for 2 hours then? Very outlier.
You're the outlier or they have a lot of samples.
Okay.
So you have an average of 45 minutes, and it has a standard deviation of 12, which means every plus 1 standard deviation, you go up 12 minutes. So the 12 plus this, 57, 69, was that the 81? Those are 3 standard deviations up. 33, 21, and 9. 3 standard deviations down. Get in, get out. Make a grocery list and go.
But then forget to get something for dinner, so then you have to go and grab like the ingredients and check it.
That never happens.
Or you have to keep going back in for 9 minutes and then coming out.
Yeah. So, when you start thinking, what's the percentage of shoppers are between 33 and 57? That's plus or minus 1 standard deviation. 68%. Between 45 and 69 minutes, between these two. Well, we know that that's 0.34, and that's is it 13? You add those together. Well, I didn't mean to put the extra decimal point. So 47.5% of data is between those two. It's just a matter of adding up percentages. Okay? That's all norm data is. If you can norm your data, these percentages never change. That's why people spend all that time in stats classes learning about how to do that. What's that?
Memorize the percentages.
No, all you have to know is 68, 95, 99, 7.
Okay.
I showed you how to subtract to figure them out.
Yep.
That's all you have to know how to
It's
do.
easier just to memorize like the four
Why?
numbers.
Why?
But you don't have to do math.
68, 95, 97, 99, 7.
Then you still have to do math.
Okay.
Yeah.
I mean, really, you're right. It is only 4 numbers.
Yeah,
I mean, it's
so
not
probably
that bad.
pretty easy to like memorize.
I mean, really, if you really want to get fancy, don't you really need to know 3 of them and know that the other one's going to add up to 50?
Yeah.
What's the probability?
Probability? What's the probability randomly chosen shoppers spends between 45 and 69 minutes? Well, what's 34% and 13.5% added together?
Math. You just add them.
Yes, ma'am.
You can use percentages.
Yeah. Yeah. Or decimals is fine. A lot of times they talk about this within percentages. Okay.
Homework?
They're saying that, excuse me. Oh, it's making you have to calculate it. I'm not going to make you calculate any of that.
You just keep that like banana. Also, you can stand it up
Yep.
She's like, wait.
It works out to be, I forgot what page it was, but it's 23 through 28, and then 38 to 43. Sure. Yes. I don't know. Some page, 1.7 page. 750 or 850 or something along those lines. I forgot. I will tell you. $750. But seriously, guys, if you know 68, 95, 99.7, that's what you have to know.
Oh, I'm reading
Okay.
wrong.
All right.
Can I like read 20?
Oh, norm data.
I keep thinking of a robot.